For the next few weeks, we're going to be talking about problems that make the assumption of constant acceleration. That means that the acceleration is a number and it doesn't change. The acceleration neither increases nor decreases. Maybe it's 0, maybe it's 4, maybe it's 9.8 meters per second squared. That's the acceleration due to gravity, and we'll talk a lot more about that next time we meet. But constant acceleration just means that the acceleration does not change. It stays the same. So let's jump right in. First thing we can talk about is that when there is a constant acceleration, well, let me back up. We automatically know just from prior experience that average velocity equals delta x over delta t, right? Change in position over the change in time. We talked about that last time, okay? When the acceleration is constant, we can also talk about average velocity this way. Average velocity can also be initial velocity plus final velocity divided by 2. You can actually just average the initial and final velocity and divide by 2 when the acceleration is constant. You cannot do that if you have a variable acceleration, only when you have a constant acceleration. So this is a new definition for average velocity that only works when we have constant acceleration. Well, let's see what happens when we set those two things equal to each other. So they're both average acceleration. So we can say the change in position, change in displacement over the change in time equals VI plus VF divided by 2. Interesting. So if we wanted to solve for the change in displacement, which would be how far we moved, we could multiply both sides of this by delta t, right? Multiply this by delta t, multiply this by delta t, cancels here. So we would get delta x equals, I'm going to clean this up some, 1/2 VI plus VF times delta t. So now we have an equation where, given constant acceleration, we can find displacement from initial velocity, final velocity, and time. We can also rearrange this equation and solve for time. We could rearrange it and solve for initial velocity. We could rearrange and solve it for final velocity. So let's do a couple quick examples of this with this equation. So let's work this problem. The problem says a racing car reaches a speed of 42 meters per second. If, I should say it, and I can't type, it, I'll just ignore that. It then begins a uniform negative acceleration using its parachute and braking system and comes to rest 5.5 seconds later. Find the distance that the car travels during braking. Now, I already told you that we're going to be using the formula we just talked about, which was this, delta x equals 1/2 VI plus VF times delta t. Okay? So we need to figure out what we know already. Well, what are our knowns? I'm going to put the knowns in green. And we'll try to stick to that, just so you'll know what you're looking at. Well, I have a velocity. Is this an initial or a final velocity? Well, we're not sure. Is this at the beginning or at the end of the acceleration? Well, it says it slowed down. So we started at 42 meters per second. So that's going to be our initial velocity. 42 meters per second. Okay. What else do we have? I see 5.5 seconds. That sounds like a delta t to me. So we have delta t, which is 5.5 seconds. What are we being asked for? It says find the distance. Distance the car travels while braking. That sounds like delta x. That sounds like displacement, and we don't know it. That's what we're going to look for. Well, okay. We're almost there, but we're missing something. What are we missing? We're missing final velocity. So we need to know the final velocity. Well, what happened in this situation? It says it begins a negative uniform acceleration using its parachute and braking system and comes to rest. Comes to rest. What does that mean? That means it stops. How fast are you moving when you have stopped? 0 meters per second. So we have all our knowns. We know what our unknown is. So we can plug in. Great. So delta x, which is what we're looking for, equals 1/2 times vi, which is 42 meters per second, plus vf, which is 0 meters per second, times the change in time, which is 5.5 seconds. Let's do some arithmetic here. 1/2 42 meters per second plus 0 meters per second is just 42 meters per second times 5.5 seconds. All right. 42 times 5.5 is, oh, I should be able to do that in my head. Oh well. 1/2 times 42 times 5.5 ends up being 120 meters per second times seconds. I'll do a side problem over here in blue. We've got meters per second times seconds. The seconds cancel, so we end up, because that's on the top of a fraction, that's on the bottom of one, they cancel, so we end up with 120 meters as our distance. 120 meters. And distance is supposed to be in meters, so we know we didn't screw anything up. That's how you do this kind of question. Let's do another. Okay, here's another one. It says a car enters the freeway with a speed of 6.4 meters per second and accelerates uniformly for 3.2 kilometers in 3.5 minutes. How fast in meters per second is the car moving after this time? Now we got a few things going on here. So let's start by writing our knowns. Again, we'll put our knowns in green. Well, what do we know? We know enters the freeway with a speed of 6.4 meters per second. That sounds like an initial velocity. That's what we started with. 6.4 meters per second. Alright, accelerates uniformly for 3.2 kilometers. That sounds like a displacement. 3.2 kilometers. In 3.5 minutes. That sounds like a time. That's pretty straightforward. How fast in meters per second is the car moving after this time? Well, after a time, that would be a final velocity that we're looking for, and we don't know it. Okay? Alright, great. Sounds like we can just plug in. So delta x equals 1/2 vi plus vf times delta t. Alright, we're looking for vf. So let's solve this equation for vf. So we got to get vf by itself. That means we got to get everything that's not vf away from that side of the equation. Alright, I'm going to switch to yellow to do this work. So I'm going to divide both sides by delta t. Divide by delta t. Delta t cancels, so we end up with delta x over delta t equals 1/2 times vi plus vf. Okay, now you get rid of that half, so I'm going to multiply both sides by 2 times 2. So I end up with 2 delta x over delta t equals 1/2. Oop, nope, we got rid of 1/2. That's what we just did. So it just equals, so those cancel, vi plus vf. Okay, so now that means that we can subtract vi from both sides. That's vi. And get vf, I'm just going to flip the equation over, vf equals 2 delta x over delta t minus vi. So that's the formula we actually want to use. I'm going to clean this up. Much better. So Now we just plug in. Great, let's do it. So VF, which is what we're looking for, equals 2 times delta x. Delta x was 3.2 kilometers. Uh-oh. We can't have kilometers. We need to be in meters per second. We need all of our units to agree. So we've got to convert 3.2 kilometers to meters. Luckily, that's easy. We know that that's just 3,200 meters. Okay, crisis averted. 2 times 3,200 meters divided by time, delta t, is 3.5 minutes. Oh, but we need that to be in seconds. So we got to convert, but that's pretty easy. We know that there are 60 seconds in a minute, so we can break out the calculator and take our 3.5 minutes, multiply it by 60 seconds. And if you need to do a conversion factor, great, but I assume all know there are 60 seconds in a minute, and we get 210 seconds. Okay. Crisis averted, chapter 2. Divided by 210 seconds minus your initial velocity, which was 6.4 meters per second. Notice that when we divide this distance by this time, meters per second, we'll end up with meters per second minus meters per second so that it stays the same. So we actually get a velocity at the end that's going to be in meters per second. So let's crunch these numbers. 3,200 times 2 divided by 210 minus 6.4. So we end up with about in the neighborhood of 24 meters per second. And there's our answer. And I hope I didn't make a mistake. I'm sure you'll let me know about it if I did. Okay? But it's really important, especially at first when you're working these problems, to write down your knowns real clearly somewhere. And I really recommend that you do the algebra first when you have to rearrange an equation, because if you plug those numbers in first, it's so easy to forget a sign or to forget a 2 or to have an extra 2 or something like that. So I really recommend that you rearrange these formulas first before you start plugging in. Okay, let's move on. All right, let's now consider the acceleration equation, which said that acceleration equals change in velocity over the change in time. Well, and we know that change in velocity is really Vf minus Vi over t. So we can compress this and write A acceleration equals Vf minus Vi divided by delta t. We'll keep it as delta t, just because that's what we've done so far. All right. If we multiply both sides of this equation by delta t, cancels over here, we can end up with A delta t equals Vf minus Vi. And we can solve this for Vf by adding actually Vi to both sides. It cancels over here. So we can get another new equation, Vf equals Vi plus At. Final velocity equals initial velocity plus acceleration times time. And I keep forgetting to make this delta t. Do this way. There we go. Okay, there's another new equation for Vf, Vi, A, and delta t. And we'll use it in just a moment, so make sure you write it down. And it's not hard to arrive at. You should be able to derive this if you absolutely needed to. So let's do another. For this one, we need to start with our previously two derived equations. So we're going to start with the one we just did, which was Vf equals Vi plus A delta t. And we're also going to use delta x equals 1/2 times Vf plus Vi times delta t. All right. what we're going to do here is this. We're going to substitute this into here for VF because, well, VF equals that, so we can do it. So this is what it's going to look like. We're going to have delta x equals 1/2 times, instead of VF, we're going to write VI plus A delta t. So that's just this part. We still have to add VI plus another VI, the one that was already there. This one got plugged in. This one was still left, times delta t. Oh, well, that's ugly. Well, let's see what we can do. So we get delta x equals 1/2 times, let's see, I get VI plus VI. That's VI plus VI is 2VI plus A delta t times delta t. Okay. Well, we need to distribute from both sides, so let's distribute the delta t first. So we still have our delta x equals 1/2 times. Distribute the delta t gives us 2VI delta t plus A delta t times delta t, so plus A delta t squared. Delta t squared. Okay, close parentheses. Now we have to distribute the 1/2. So we're going to finally end up with, oh, I wrote an A, delta x equals, well, half of 2 cancels, so VI delta t plus 1/2 A delta t, and that delta t is squared. And this is our formula that we're going to want to use. Notice how this formula gave us VF, VI, A, and T. This one gave us delta x, VF,